Good afternoon, Bobcats. Today we will be discussing Hess's Law. Now, since enthalpy change, or delta H, which we call delta H, is a state function, and does not depend on the pathway, we can sum up the enthalpy changes of several chemical equations So we can sum up the delta H, or enthalpy change, for a series of chemical equations to find the enthalpy change of an overall reaction. So chemical equation to find the enthalpy change of an overall reaction. Regardless, remember, because it's a state function, it's not a pathway, we can do this regardless of whether those steps are actually involved in the reaction mechanism. So let me state that again so that we understand, we get an idea. So because enthalpy change, or delta H, is a state function and it does not depend on the pathway, we can take several different chemical equations with delta H values and add them together to get the delta H value of an overall reaction. And it doesn't matter whether those steps are actually involved in the reaction or not, because remember, it's a state function and it doesn't matter about the pathway. And in general, we can say that the delta H, or enthalpy change of a reaction, is equal to the enthalpy change of reaction 1 that was used plus reaction 2 plus reaction 3, and so on. However many reactions are involved in that enthalpy, determining that enthalpy change. So to give you an idea of what we're talking about, let's say I want to know the enthalpy change of this reaction. We have nitrogen gas plus 2 moles of oxygen gas goes to 2 moles of nitrogen dioxide gas, and we want to determine the delta H of this reaction. Okay. So, and I'm going to underline it as if, so we know that that's my original reaction I'm looking at. But we're given these reactions to work with. So we have nitrogen gas plus oxygen gas produces 2 moles of nitrogen monoxide gas, and that has a known value, delta H value, of a positive 180 kilojoules. And then we also have this reaction that we can work with. 2 moles of nitrogen monoxide gas plus oxygen gas goes to 2 moles of nitrogen dioxide gas. And this has a known enthalpy change value of negative 112 kilojoules. So now what we need to do is we need to add these reactions together. So when I do that, I'm going to add these two together. And when you add reactions together, you can cross out the reactants and products that are on this. If I have a reactant on one side and I have a product as a reactant, I can cross them out. So if you look at this, I notice that 2 nitrogen monoxide gas, 2 moles of nitrogen monoxide gas is a reactant. We also have 2 moles of nitrogen monoxide gas as a product. So I can, and you can kind of think of it as we're adding these together. And so those are gone, they cancel each other. It's just like if you have 2 on each side of an equation, you can cancel it, or if you have an x on each side of the equation, you can cancel it. And then we add them up. So when I add this, we have nitrogen as a product, plus, and now there's 1 mole of oxygen here, plus 1 mole of oxygen here, so that's 2 moles of oxygen gas, producing 2 moles of nitrogen dioxide gas. And my delta H for this of the reaction is just, I add the delta H of 1 plus the delta H of 2, which is 180 plus negative 112, and so I get a positive 160 kilojoules of energy. Again, I just add 180 plus a negative 112, and that gives me positive 68 kilojoules per mole of kilojoules for this reaction. Okay, now that is simple. We didn't have to do anything. We didn't have to change or manipulate any of this. We just had to cancel what was on the same on both sides, just like we do with ions and spectator ions and so forth. But what if sometimes you have to manipulate or rearrange equations to get the equation you want to find the enthalpy change for. So the next thing we need to look at is this. Let's use this page still, since I still have this page. Let me draw a line underneath. Okay. So given reactions, remember these are the given reactions. So given reactions may have to be manipulated or rearranged in order to get the desired reaction. Now, when we do this, there's a few things that we have to be aware of. Oops, reaction. Okay, desired reaction. First, you need to decide how to rearrange equations so that reactants and products are on the appropriate side. Next, what you have to do is, if the equations are reversed, the sign of the delta H must also be reversed. Okay. Two more things we need to consider before we practice again. And so first we have to just decide how to rearrange the equation so that the reactants products are on the appropriate side. If you have to reverse the equation, a positive delta H becomes a negative delta H and vice versa. If the equations are multiplied, to get correct coefficients, then the delta H is also multiplied. Okay, and that also applies for dividing. So division is similarly applied. Okay, and then last, what you should do is you should check to ensure everything cancels out to give the exact equation you want. That includes states of matter and everything. So now what we need to do is practice, do a couple practices to make sure that we can do this. So let's do a practice problem right here. So I'm going to use a couple of different colors and show you the process at which I do this. So with this practice one, we're going to start out with 2 moles of sulfur trioxide gas decomposes to make 2 moles of sulfur dioxide gas and 1 mole of oxygen gas, O2 gas. Okay, that's O2. And we are looking for the delta H of this reaction. What is the delta H of this reaction? Okay, so we're going to have a given. So this is what we're looking for. We are given sulfur solid plus O2 gas goes to sulfur dioxide gas, and it has a delta H value, and we'll call it reaction 1, delta H value of a negative 296.8 kilojoules. And then the other given reaction is sulfur solid plus 1.5 or 3/2 moles of oxygen gas produces sulfur trioxide gas, and that has a delta H value of negative 395.6 kilojoules. Okay, so now I'm going to have to manipulate these. So then I do a whole nother row of this because it's really hard to keep track of if you're not very careful with it. So then this is, how do we want to call this? We'll say this is the rearranged equations. Rearranged. Okay? So in this, I notice that I have sulfur dioxide on the product side. I need it on the product side because I want it on the product side. So I'm not going to flip it, but I need 2 moles of it. The given one only has 1 mole. So I'm going to multiply everything by 2 all the way across. So it's going to be 2 sulfur solids plus 2 oxygen gases produces 2 moles of SO2 gas. And then I also have to multiply my value. I'm not going to put the units in right now. We're running out of space. Now that matches. So if you'll notice, I've got 2 moles of sulfur dioxide gas on the product side. I now have 2 moles of sulfur dioxide gas on the product side. Let's look at the other one. I need my sulfur trioxide. Here it's a product. I need it on the reactant side. So I have to flip it. And not only do I have to flip it, but I also have to multiply everything by 2 because I want 2 moles and I only have 1 mole. So I'm going to flip it and write it. Multiply by 2. So that's 2 SO3 gas produces 2 moles of sulfur solid plus, and 2 times 3 is 6, and 6 divided by 2 is 3, so that's going to be 3 moles of O2 gas. And in my delta H for this reaction, of course, I had to multiply everything by 2, and not only that though, I had to change the sign, so now it becomes a positive. It was negative, now it's positive. Okay, and so again, I've got the correct reactant and the correct product. Okay, so I'm going to start canceling, and I'm just going to kind of do a division line here so you can keep them apart from each other. Okay, now to cancel and to add it up, so I'm going to add it up here, so, and say kind of a plus sign, not that you really would show that, but I'm just kind of showing you that we're adding it. So I've got 2 sulfurs on the reactant side and then 2 sulfurs on the product side, so those 2 cancel. And then I have 2 oxygens on the reactant side. I have 3 here, so these 2 are canceled and the 3 goes to 1, so we can say we canceled the 3, so it's just 1 oxygen. And then nothing else can be canceled. So now I write it down. So on the, if you look at it, I've got these are products, right? This, and this. These 2 are gone, so my only product left, reactant, sorry. My only reactant is SO3 gas, and it goes to, well, we've got a product here, 2 SO2 gas, and then I look down here and I have 1 mole of O2 gas. And does that match the original? So I go back up and I look, 2 SO3, 2 SO3s, 2 SO2, 2 SO2, 1 oxygen, 1 oxygen. And now I just, for the reaction, delta H of the reaction, I just add and multiply and add those up. So that will come out to be, so I have 2 times a negative 296.8, and then 2 times a 395.6, and then I add those 2 values up, and I'll just write it down here so you can see that what we're looking at is the delta H of the reaction is equal to 2 times a negative 296.8 plus 2 times a positive 395.6, and if you, this is a negative 593.6 plus a positive 791.2. So my delta H of this reaction is 791.2 minus 593.6, and I get a positive 197.6 kilojoules per mole. And usually I don't show all of this work, I just do it in a calculator and add those 2 values up and just write it down over here. Okay, so this is the process. Remember, you have the original equation right here. This is my original equation. That's what I'm looking for. I have the two given equations, and then I'm going to call this area the rearranging or manipulation equation. So I make sure that this SO2 is on the same side, so I don't flip it, but I have to multiply everything by 2. So I do that. I also multiply that 2. This, my SO3 is on the product, but I want it on the reactant, so I flip it. And then I also need 2 moles, so I multiply everything by 2. Now we're going to do one more practice problem for this one, and it's going to be just a little bit more. You notice how there was 2 given reactions here? The next problem is going to have 3 given reactions. So let's try to keep track of 3 given reactions. Now, let's see, the original equation is going to be dinitrogen monoxide gas plus nitrogen dioxide gas produces 3 moles of nitrogen monoxide gas. And we want to know what is the delta H of this reaction. Don't know it, so we're looking for it. So I'm going to just underline it to show you that this is the one that we want to make sure we end up with. Now here's the given. So the given ones, we are given nitrogen gas plus oxygen gas produces 2 moles of nitrogen monoxide gas, and the delta H value for that is equal to, and we'll call that reaction 1, a positive 180.7 kilojoules. The next reaction is 2 moles of NO, or nitrogen monoxide gas, plus 1 mole of oxygen gas produces 2 moles of nitrogen dioxide gas. And that has a delta H value, and it's a reaction 2, so a negative 113.1 kilojoules. And then my third reaction that's given is 2 moles of nitrogen dioxide gas produces 2 moles of nitrogen gas plus 1 mole of oxygen gas, and it has a delta H value of a negative 163.2 kilojoules. Okay, so those are the given ones. Now I'm going to have to manipulate them, so it's easier if I just do a whole nother step where I manipulate it. And so we're going to call these the rearranged, or however you want to call it, rearranged ones. Okay, so now we've got, if I notice here, I've got the nitrogen monoxide and the nitrogen monoxide. But I know it's a 2 and a 3, but I'm not going to multiply by anything because I also know that I have a nitrogen monoxide over here. And so I may end up getting the number I want without having to multiply this. So first I'm just going to rewrite it. Since I'm not going to flip it, it's on the right side, the correct side, so it's going to be nitrogen gas plus oxygen gas produces 2 moles of nitrogen monoxide gas. And my delta H didn't change for this at this point. A positive 180.7 kilojoules. Now the next reaction, let's see how we can manipulate that one. I know that I need to see the NO2 as a product here. Up here, NO2 is a reactant. So I need to flip this. Not only that though, this only has 1 mole, this has 2 moles, so I have to divide everything by 2 or cut it in half. So I'm going to flip and divide by 2. So when I divide by 2 and flip it, that'll be NO2 gas, 1 mole instead of 2 moles, produces, 1 mole of NO gas plus 1/2 of a mole of O2 gas. And the delta H for this, and I'm trying to keep my arrows all straight as possible. My delta H for this one, I had to flip it so it becomes positive, and then I divide by 2. So when I flip and divide by 2, I get a positive 56.55 kilojoules of energy for that reaction. And then the other reaction, NO2, well, I've got it on the correct side. The N2O here, the dinitrogen monoxide gas, is a reactant, and in the original equation it's a reactant. So I'm not going to flip it, but instead of having 2, I only want 1, so I'm going to cut everything in half again. So we're going to have N2O gas produces, oh, I forgot to line up my arrows, sorry about that, produces 1 mole of N2 gas and 1/2 of a mole of O2 gas. And then my delta H, or my enthalpy, is going to be, well, I didn't flip it, so I keep the same sign, but I have to cut it in half, so it's going to be a negative 81.6 kilojoules. Now I'm going to add all of these up. You can think of it as adding it up, and so I have to cancel everything. Okay, so let's go through and start canceling. I have an N2 as a reactant, and this N2 is a product, and it's only 1 mole, so that cancels. I have 1 mole of O2 here as a reactant, and then 1/2 of a mole and 1/2 of a mole makes a 1 mole of oxygen as product, so this one cancels both of these. And then we know that if we look, I can't cancel anything else. That's okay. That's good. Everything is good there. So now I'm going to write it out as if to see if it matches the original. So these are gone. This is a product here, and this is a product. So I'm going to write it as N2O. I mean reactant. I said product. I meant reactant. I'm sorry. Plus NO2 as a reactant produces N2O, 2 moles of NO here and 1 mole, so those two add up to make 3 moles of NO gas, right? 2 moles here, 1 mole here, that adds up. There's no other reactants. Let's see if this worked. 1 mole of N2O, 1 mole of N2O. 1 mole of NO2, 1 mole of NO2. 3 moles of NO, 3 moles of NO, and so my delta H of the reaction, and all I'm going to do is just add these up, and so that comes out to be a 180.7 plus 56.55 minus 81.6, and I'll get a positive 155.65, but we're going to round it to 7 kilojoules, and that's the answer. And that's how you go about doing it. And so first you have the original equation, then you have the given ones with their values, and then we have to manipulate or rearrange the equations to match the original, and then cancel, or you're adding them, but by adding you're canceling everything, and then just adding these two and then adding those two to get the product, and then you add the values. I'm just going to kind of draw a dotted line here so you can see that there's a difference there. Okay, and that is Hess's Law, and I will see you next video.